So welcome to what is going to be the last lecture of the coq intensive. This afternoon we're going to, I think after the homework session, we're going to switch into the summer school proper, and Professor Appel will be presenting sort of a deep spec overview and give some hints of what's to come in the next week and a half. Before I begin, are there any burning questions that anyone wants to ask about any of the material we've covered so far? If not, there'll be an opportunity during the homework session to follow up. Okay. So, right. This last lecture is going to be discussing how to further automate your proof scripts using this powerful tactic called auto. So you saw in Professor Appel's lecture yesterday a variety of tactics that you could use to further, and tacticals that you could use to build more adaptable, effective proof scripts, shrinking down these sort of long, these rather long manual proof scripts and things that are much shorter, that are more adaptable to changes in your definitions and specifications. And today we're going to consider what is one of the main workhorses for automating your proofs, again, auto. So just to begin, what we're going to do in this lecture is we're going to take this proof that we saw in the last lecture that Leonard gave, showing that the evaluation rules we gave for IMP are deterministic. That is, for any given program C, if it's run in the same starting state, it will always arrive in the same final state, right? That is, assuming it finishes. Okay. So it's worth just stepping through this proof, I think, in a little bit of detail so we can appreciate exactly where the automation is going to kick in. By the end of this lecture, this will be down to a single line of proof script using auto, and we will have a few custom handwritten tactics in LTAC, and we'll adapt this to a different definition of the IMP language, which has a new construct, and the automation will more or less handle this new case effectively. So let's just begin. So here's the proof. There's nothing too exciting about it so far. It will proceed by induction over the first derivation the first proposition that C evaluated some state. That's what this induction is. We'll do inversion over the second derivation to make sure everything syncs up. And then we have a bunch of cases that roughly correspond to the different statements that were used to define the program. So as an example, in the first case, we're going to have skip. There's only one rule that applies, and that you basically end up in the same state, so nothing interesting happens. Assignment is similar. For sequence, we are going to assert some intermediate equality between the states that were arrived at between when we stepped with the first sequent and the second one. We do an assertion, we're going to apply an induction hypothesis, so on and so forth. We'll rewrite with it, we'll apply the second hypothesis, we'll use assumption. And this is more or less how we're going to proceed. We'll be applying the induction hypothesis, we'll be using assumption for the if case, we'll do a little bit of rewriting, we'll do some inversion, so on and so forth. And eventually, I keep talking and I keep processing, and we're going to get to the end here, I hope. Soon. Yep. I do some rewriting, we do some more assertions, we hit QED. Okay, and at the end of the day, you'll note that a lot of this proof it felt very similar, right? There were some applications, we called assumption on occasion, we did an assert in a couple of cases, we did some rewriting, but it was all fairly straightforward. And as you step through it, it would sort of, you could sort of see how ideally, you could just, if there was some way of canning together sort of a recipe for solving these goals, we should just be able to apply that recipe once and for all and discharge that. And that's exactly what we're going to do with auto. So this is the proof we're going to be automating. Let's start off with a simpler example of how auto works. Okay, so in that proof script that we saw, and indeed in many of the proof scripts proofs we've written so far, we have this flavor where we intros, the hypotheses. That tends to be the first tactic you always run. And then you apply either one of those hypotheses or some sublemma that you proved in some other place, right? So in the case of auto example 1 here, what do? Well, we do exactly that. Well, we have a goal that looks like R, so we know that Q implies R. We'll apply that hypothesis. We'll apply the next one, and then we'll call assumption. Again, what does assumption do? It just looks in our list of hypotheses or assumptions, sees if there's one that more or less precisely matches the goal, and just applies it for us automatically. And this has this nice feature of us not needing to explicitly say apply H3. Okay. So we could also use auto to do this. So instead of doing intros and manually applying things and calling assumption, auto will just magically solve the goal. Done and finished. So how does auto work? So here's the basic rule of thumb. This is the first approximation, and we'll see how this get into a little bit more detail. But for now, you can imagine auto can solve any goal that has that you could solve by saying intros, and then just applying things in the hypotheses by default. We'll see how to add other things that it can attempt to apply. All right. So. And the show proof result would be identical. Yes. So in this case, we could actually print auto example 1 prime, and it's going to look exactly like apply. These are the relevant bits here. We're going to apply the H0 hypothesis to the result applying the H hypothesis to the H1 hypothesis, which this is P implies Q, and this is Q implies R. And if we print it out, just the regular auto example, indeed, well, the hypotheses have different names, but that's life. Morally speaking, it's the same thing. Up to alpha equivalence, these are the same proof term. Okay. So more interestingly, suppose we had this slightly more complicated goal, where you can imagine it's going to involve several sequences of apply over and over, and auto is just going to solve this. It's just going to intros everything, and it'll just start applying things until it can solve the goal. An important property of auto is that it will either completely solve the goal, or it will leave it unchanged. Right? You will never get into an intermediate state. So, and it will never fail. So it's always safe to put auto on the end of any proof tactic that you're running using the semicolon tactical. It won't. The worst thing that could happen is that it leaves the goal unchanged. Okay. Well, yes, that's the worst thing that happens. Yeah, there's a question.
Trivial was kind of like the same thing. How did you crack, or just do it around halfway?
Yeah, so the question was, how is the trivial tactic different from auto? Did you cover trivial in the previous? No, okay. Well, you can read more details in the coq documentation. They have a lot of details about how these tactics work, but indeed trivial is basically a simpler version of auto. This is the way to think of it. So I think trivial doesn't consult the same. Yes, let's go with that for now. And we can revisit, ask me that question at the end of the lecture after we've talked about some more features of auto, and I can give you a more detailed answer. Are there any other questions about auto? Okay. So, right. So there is one little tricky bit about how what auto is doing here. So it intros everything, and then it just starts supplying things, as best it can. And as you can imagine, it is possible, if you have some sort of wacky hypotheses, that it could just keep repeatedly applying the same hypothesis to the goal over and over and never terminate, which would be bad because then auto would never return. It would just sort of hang. And so by default, auto has a limit on how many times it will try and use the apply tactic before it sort of backs out. By default, that number is 5. It will try and use apply for different combinations of hypotheses or lemmas 5 times. If it doesn't solve the goal, it backs out. Oh, that's okay, yeah. So here's an example of where this is slightly problematic. So here, if we try and call auto on this goal, it's not going to It's not going to solve it. Why is that? Well, it's because it needs to apply 1, 2, 3, 4, 5, 6 hypotheses in order to solve the goal. But we can give Otto an optional argument that tells us how far in this search tree it should work. So if we say Otto 6 here, it works. No problem. Okay. In many cases, 5 is fine, surprisingly. Very, very rarely will you go beyond 10. So what is, it's important to come up with sort of a conceptual model of what Otto is doing under the hood. So what does Otto do in a little bit more detail? Okay, so it's going to intros everything into the set of assumptions above the line, right? And then it's going to look at the conclusions of all of the things that it knows about. And it's going to see if any of those match the goal in a certain way, look similar to the goal. If one of them matches, it will apply it, and then it will recurse. And it will do the same thing, compare the set of assumptions against this new goal for all goals generated, and try and apply. And so you can imagine it's recursively building up this proof tree under the hood. It's just a bunch of different applications at each step. Okay. Now, as you can imagine, this proof tree could go quite large, particularly if you have sort of a breadth first search where there are a bunch of different hypotheses that could apply at every step. So if it gets to a node and it's hit its bound and hasn't solved the goal, it's going to back out and try to apply a different matching hypothesis at the same depth and go up. And so eventually, it could build up a very large proof tree. So this is why it's important to bound the depth. So I'm going to give a little example of this in action. Okay, so here's another example of where you need to supply a specific proof bound. Okay, so Otto doesn't work, Otto 6 works. Here's a more interesting one, which is going to be sort of pathologically unpleasant. Yeah, so this is going to be pathologically unpleasant. So looking at this example right here, what are we going to do to solve this goal? Well, we need to apply H2 5 times, right? So we're going to get a new subgoal P4, P4, P3, P2, P4, P3, P2, P1, P0. So 5 times to solve the goal, right? Okay, right. So the number of times you need to apply it is the number in the goal, the original goal, plus 1, just to be safe. Okay, so let's look at this goal. So here, suppose I'm going to get rid of these ands because that's not too important. Suppose we had P10. So here we're going to need to go to depth 11 in order to make this work, right? Okay, that's good. But now we have this problem, right? If we set our bound a little too small, we're never going to get to P0 when we can apply H1. So we're going to go, intuitively what's going to happen is we're going to go all the way up the left branch, applying H1 all the way, but we're going to hit our bound before we apply H0. And then we're going to back out, and now we're going to try and apply, H2, and that's not going to work. So then we'll apply H2 prime. That's not going to work because we hit the bound in every case. Then we go back down. And the first application of H1 didn't work. So we're going to go over here and we'll play H2, and then we're going to replicate this proof tree. So you can imagine this is going to be quite inefficient. So in fact, if we don't give a large enough bound, well, mine is a little, I don't know if you noticed, but it took a little bit of time for coq to process this command. Even though if we'd set the right bound, it would have solved it completely. Okay. And if we had a larger number here, let's go with 20 and 19. Am I going to want to do that? This proof search can actually take a very long time before the goal is not solved. And in fact, it's going to take so long that I'm not going to process it anymore. The irony, of course, is that 21 would have solved it completely, but that's life. Okay. So this is important to keep in mind. If you have, part of the reason that this was so inefficient was that there were multiple different things that could be applied to the goal at each step. And if we didn't solve the goal, there were a lot of alternatives to choose from in terms of what to apply. And Otto just tries to apply everything it can at each sort of recursive step. This is problematic. Okay, so keep that in the back of your head. Okay, so we can actually, right. So in addition to the hypotheses that are in scope when you're working on a particular proof goal, Otto has a set of databases of facts and of lemmas that it can try and apply to the goal. There is a default hint database of facts that it will always try and apply in addition to the assumptions you have in hand. And as we note here, in particular, facts about equality and logical operations like and or are just baked into Otto by default. So as an example right here, Otto is going to solve this goal because, we could actually see what it does. I'll do that in a second. What is it going to do? Well, it's going to apply the constructor for OR to split off into two sub-goals, and then it's going to recursively call Otto itself on that, and it has a rule about how to deal with ands, so it'll split off a sub-goal for each of those ands, and solve, and eventually resolve the goal using the hypotheses it has in hand. So if we use this info, if you append info underscore before Otto, it will actually tell you exactly the sequence of lemmas that it applied to solve the goal, which is unfortunately a little small here, but I'll blow it up. So you can see what it did here. Again, what is it doing? It's just applying intro a bunch of times. I don't know why it does this instead of intros, but whatever, it's morally the same. It might be because intros expands in intro, but I'm not sure. So it's going to apply the constructor for or intro. This core is the name of a hint database. Don't worry about that right now. It's going to apply the rule for the constructor for ands. Then it'll call assumption. It'll try to apply one of the assumptions we have in hand, and then it'll solve the resulting goal with assumption. Okay. Yes. Any questions so far? So Otto, one second. Otto is going to solve a lot of things that it should by default. You just look at it and you're like, it should probably solve this. And Otto, so let's say 65% of the time will solve the goal for you. Yeah?
So in general, tactics are not guaranteed to be terminated, right? So
yes. Okay, so one question. So the question was, in general, tactics are not guaranteed to terminate. The answer is yes. Next question.
no, so I was going to say, so if you have some automated, some group with automation and you make hand, right? And then you have the tips on how to debug this, like,
the question was, if your automation is hanging or buggy, do I have any tips for debugging it, debugging these tactics? And the answer is, ask me that again at the end of the lecture. And it can be not a lot of fun, but there are a couple of tricks that you can use to make it less painful. So actually, on the fly, no. I was going to write down a tactic that will hang forever, but I don't want to do that right now. So ask me again at the end of the lecture, and I'll write a quick tactic that hangs forever, and we can debug that. It shouldn't be too hard. Don't call it. Okay, so again, so what does Otto do? It tries to solve the goal by applying stuff in the hypotheses you have in hand of the current goal, and it tries to apply lemmas or facts that exist in one of its known hint databases, right? But you can also add new hints to the database using a couple of different commands. So one way to do it is if using this variant of the tactic called auto using ... So as an example, we have this proof here of the anti-symmetry of less than or equal to, which just says that if n is less than m and m is less than n, then n and m are equal. Okay, right? And we can actually use this to solve this goal pretty straightforwardly. So if we extend, we can tell the auto tactic to use this fact when it's trying to, or consider applying this particular lemma when it's trying to solve this goal, saying using LE anti-sim. And we could actually put a comma here and add arbitrary other lemmas, like our little example from above. This will work. So you can actually add as many sort of hints, local hints to the database about theorems to apply using this using tactic. Okay. Yes?